Okay. So I'm Ward, and while we were going through this, it occurred to me what the order was. Of course, we had students of Heinrich, then we had a postdoc of Heinrich, and we've got somebody who was both a student and a postdoc of Heinrich's. So I work for NVIDIA, and what I do is I work out wave optics problems and holography problems for NVIDIA. Right? And those of you who know NVIDIA know that it's doesn't do that stuff usually. So we'll get to why it might be interesting to NVIDIA later to work out holography problems. But when Jaumin asked me to do this, I sort of asked, what do you want me to talk about? And he said, put yourself in sort of a grad student's shoes and ask yourself what they might be interested in. And at the time, when I was sort of finishing things off, I was looking for a job. My questions were all about how, right? How do you find an industrial job if you want that? And how do you convince somebody from industry to hire you, right? So let's start there, right? And specifically, let's start talking about how you do the application process. What I put up here is basically, at the time when I was applying, what people thought, or at least what everybody around me thought, was sort of the consensus view, right? What's missing here is you find some listing of an industrial job, right? Then you build a cover letter and a CV. You send that off to somebody, probably in HR, right? And then you get an interview, and then things go well, and you get a job. I don't know anybody who has a PhD who got a job that way in industry. Right? There may be people out there, but I haven't had conversations with them about their process, right? That says this is the way they got a job. So that's not the way. Like, what is? I should say I haven't done a statistical study, but in my experience, what happens is you go through and you have some experiences that say, this is something I might like to do. Then you work a network. You talk to your friends, you talk with people that your friends know, right? And say, I'm looking for this kind of experience. Do you know anybody who could help me find out about it? And eventually somebody says, why don't you apply, right? And so that's sort of the end of the talk, but I figured it'd be useful to actually say, go through my experiences and how that happened for me. Great. I'm going to start farther back than the University of Chicago. And it turns out like I've made this transition between industry and academia 4 times. Right. So here's roughly what I've done. Right. As an undergraduate, I was at Swarthmore. I got to grad school in the usual way. Right. And then I went to a startup that started with technology that was developed here at the University of Chicago. For reasons you can ask me about later, I ran screaming. Came back to the University of Chicago for a postdoc in Heinrich's lab. And then I went and did the faculty thing and got a faculty tenure track job. And then I found out that wasn't really what I wanted to do either. So I went to NVIDIA. And what makes NVIDIA special, at least for now, is that it's essentially a research position. Right, it's basically a research institute. There are about 100 to 120 people who are basically just paid to work out problems. There are applied problems that apply to things that NVIDIA thinks might be useful to it in the future, but we're given a lot of freedom. And for me, the big difference is I don't have to write grants. Okay. So I'm going to start with Swarthmore, because another thing that I'll talk about is when you're having these conversations, it's important to tell people, or at least convey to them, that you have an interest in what you're going to be working on, or you'd like to be working on, and you can convince them that that's something you can do. Right? And some of the things that I learned in my research at Swarthmore, I still use in my job today. And so this is just a quick. I was an undergrad, I had classes to take. But I worked on this problem and I really kind of liked it. It's a simple problem. It's studying the quantum limited noise in a diode laser, right? And basically, this setup right here, that is an intensity autocorrelator. Just run quickly about how that works. You start with a diode laser, you collimate it with a lens, and the light coming out of it with a lens. You send that out into the world. You split the beam into two different beams that have equal intensity. One goes through a sort of fixed arm, right? And comes back up, and I'll get to what's happening there later. The other arm, you send along a delay. And you can just take this thing and move it. And just using the fact that you know how fast light goes, you can figure out what the delay was between the two arms. The light comes back together with the two arms. You get a lens that overlaps them in a nonlinear crystal. The original beams go off to some place and you don't care about that. But in between them, because of nonlinear mixing, you get something that is at approximately twice the frequency and has an intensity that's proportional to the intensity in each arm. Right? So you now have one intensity that doesn't have a delay, another intensity that does have a delay. That comes through here. And the PMT is just really slow, right, compared to anything that happens with light. So this guy essentially integrates over all time, and you get the average. Right? And you get fairly nice data, right? And it resolves on the length scale of picoseconds. These are all due to quantum effects that happen inside the laser itself. I don't remember much of this physics. I did this in 1993. Right. What I do remember out of this is parent feeding of this guy. Right? And what that allows me to do now is, if I want a laser, I can just take apart a projector. And I know how to turn that into what the lasers inside of it into something useful. And now I do that a lot. Okay, so from there, I came into Heinrich's lab. I worked on some problems in nanoscale self-assembly that have very little to do with optics. But what you see here, this is a diblock copolymer that's had 2.5 nanometers of silver evaporate onto it. The diblock copolymer has two different chemical species at the surface, polystyrene and polymethyl methacrylate. Turns out silver gets stuck on top of polystyrene. Polymethyl methacrylate is essentially like ice. And when you evaporate that metal onto it, you get these little globs that hang out in the polystyrene. And you can tell because the polystyrene is darker than the polymethyl methacrylate in TEM, which is how this image was taken. Because the metal itself scatters a lot of electrons, silver ends up to being really dark. Right? That thing, if you do something kind of silly, and you just keep on evaporating metal, turns out you get nanowires. This thing over here. At the time, people really wanted to make nanowires, they didn't know how. What you see in this TM that's been false colored turns out by Heinrich. This silver, we can get to that later. The silver here are these blue-silver stripes. The stuff in between it is the polymer, right? And as I said, like, what I got out of Heinrich's lab was how to do a good experiment. Not this particular, I don't do that. But okay, so while I was working on that, Heinrich was very patient with me. Every once in a while, I would go off and say, I want to find out about something else, for at least a little while. And I worked on a couple of industrial problems. Two, specifically for that couple. The new product lab, which may or may not exist anymore. They do? Okay, excellent. Would go out and get a partner. Right. that had a problem that it involved materials, involved business cases, and things like that. And they put together 6 people from the business school, 6 students from the physical science division, and they'd look at that problem and try to evaluate it and find a market for it, or find out if there was a market for it. This one was evaluating something called a polyolefin emulsion that they were hoping to use for printing problems. And we evaluated and found out that they weren't going to make any money. But they actually liked that we came up with that result. The other thing that I did was there's this company in France called Soitec. They make silicon on insulator substrates. The reason why you want that is if you're trying to make a chip run really fast, an electronic chip, right? You want your charging cycles and discharging cycles to be really short. Otherwise, you're stuck at megahertz clock rates. Right? One way of doing that is, rather, the knob that you can control is the capacitance. So you've got this deep stack of silicon, right, that conducts, and that gives you large capacitance. Right? But if you could make that thinner by, say, putting a layer of insulator on there, and then putting a layer of silicon, then you get much smaller capacitances and be able to charge and discharge much more quickly. Soitec came up with the first process to do that. They're a French company. Sorry, I'm saying, that's what I'm saying, right. And then an American company infringed their patents. And they needed some expert who knew about, they were hoping silicon on insulator substrates. As part of the work that I'd done in Heinrich's lab, I had made a bunch of insulator on silicon substrates. They figured that was close enough. So I get to the end of, I'm about to graduate. And graduation, you'll soon find out, is a busy time. Right? I thought, I'll just graduate, I'll finish up, and everything will be great. But at the same time that you're writing and defending, you're looking for potentially a new job and a career, which may or may not be in Chicago. For most of you, it probably won't be in Chicago. And if it's across the country, you have to figure out and find a place and figure out how to move there. And for me, this was the big one. Right? I had I'm trying to remember when I got married. Yeah, I had a wife. Sorry. Who was not on the same time schedule, right? And what she was saying is, I'm a teacher, hiring and firing, hiring happens on this schedule, and you dicking around trying to figure out what you're going to do next isn't going to work for me. So I had to sort of fairly quickly come up with an idea of what to do. Luckily, I'd already spent some time thinking about what I was doing because of the sort of earlier stuff that I talked about, where I was sort of exploring what was going on. Right? So I'd spent a bunch of time during that having a bunch of conversations with a bunch of people about what I was going to do next. So sort of in this diagram, time goes this way. That axis means nothing. Right? And I'm going through and thinking about what are possible things I could do in the future. This is just a good idea. As you're going along with your education, spend some time thinking about it. So I spent a bunch of time thinking about management consulting, in part because of the New Products Laboratory, and talking with folks from McKinsey and BCG and things like that. And I eventually figured out that I wasn't going to be happy with those folks, at least spending all my time with them. I probably would have been more happy doing complex fluids. I don't remember exactly why I sort of passed up on that. Turns out, being a professional expert business for most people isn't a good idea. And I also had some talks about, since I had done some work, there was a die-block startup that was happening that was going to work on some making of disk drives, problems like that. But it was decided that going on for the next thing, I'd like to try something new. So Eric Dufresne was a grad student at that time, who was just finishing up his dissertation in David Greer's lab. David Greer is now at NYU. And they had invented holographic optical trapping. This is a way of doing optical micro manipulation that depends upon holography. In case you're not familiar with that, if you start with a laser beam, put it through an objective lens that focuses it down as tightly as possible. Turns out the universe of small objects, few microns to tens of microns and smaller, turn into essentially 4 objects. Right? Ones that get attracted to the focus, ones that get repelled from the focus, ones that don't care, and ones that blow up. Right? Those 4 things are statements about the index of refraction. Blowing up is caused by having a significant imaginary part. Great. Having this thing just stay in one place isn't that useful to you. You'd like to be able to move this thing around. You can do that by changing the angle at which light enters your objective lens, and now you can just move this thing around if you're working with the collection of things that are attracted to the focus. The way you might do that is given on this next screen. Pay attention now just to the top. Right? If I work out a set of here I call them telescope lenses or transfer lenses, such that you space them from a mirror by 1 focal length here, the sum of the 2 focal lengths, and then the last focal length. But it turns out the spot here doesn't move. But if you alter the angle of that mirror, that just changes the direction at which light enters the back of your objective lens. Right? That's great. And the most obvious thing to do now is to add in more lenses, add in more mirrors, add in more beam splitters. And once you get up to somewhere between 5 and 10, you've run out of space on your optical table. Right? So if you're looking for a better way to do that, what you might do is replace this thing with something that can arbitrarily change one laser beam into as many as you want. Right? You can do that with a diffraction grating, or if you control that diffraction grating, you just call it a hologram. Right? So this is the same setup that's up here, only what I place here is my hologram. Right? And it turns out they're computer-controlled holograms called phase-only spatial light modulators. And so now, if I just know how to calculate this, I can do whatever I want here. Right? This stuff works, and we've got all sorts of, oops, wrong way, experimental evidence. These 2 things are movies. To understand what's happening in this movie next, this is approximately in focus, these 5 spots. As they change focus, if they go out of focus, they're going in and out of the focal plane. So they're changing their sort of z distance. This movie was actually taken by Eric Dufresne, and he said he'd be happy to have me just show it around. Turns out you can also change the mode of light. Right? And so if you want to, you can change the mode of light to a mode of light that carries orbital angular momentum. And when you do that, you can have one set hologram. It just spins things around, which is also kind of cool. At the time, David Greer was talking about trying to get some way to make this thing do sort of micro-scale pumping. So we know that the electric fields associated with light have both an amplitude and a phase. we're only playing with the phase. Right? We're only playing with half the information. You've got to that has to cost you something. It turns out, in the worst case, it costs you a lot. Right? So this is supposed to be a uniform Cartesian grid of light spots. This is sort of what we're trying to get towards. Right? And if you just take the inverse Fourier transform of that, like that's what you'd like to have on your hologram, you'd come up with something like this. Here I've just plotted just the phase part. And the amplitude part, it turns out, is right here. Right? That has a lot of information in it. And you would think that if you ignore that information, bad things would happen. It does. There's a spot here, there's a spot there, 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 and at the moment I can't see any of those spots. Right. That's if you do the naive thing. There are arbitrarily complicated things you can do to work on that. Those things take time to compute. Right. And if you remember the earlier videos, right, you probably don't want to take a lot of time computing things. Right? So we spent a lot of time at Eric's trying to do this computation as fast as possible. We got to a place where we were programming in assembly. You had to spend 60 milliseconds per spot. Right. So not so bad if you've just got a few. Also not so bad if you're just moving a few of them. But if you're trying to do that, kind of bad. So I was proud of that work. You might say, well, why did you leave? Turns out in small companies, personality matters. And the CEO was problematic. So I left. And so did a whole bunch of other people. So when I came back to the University of Chicago, I started working on these self-assembly problems again. These are die blocks. Steve, last time I checked, was still working on them, right? And there are interesting problems about how these things order over time. Right? Turns out, every time you take these stripes and you make them bend, that costs you energy. And at fairly low energies, the question is, how do these things order over time? And there were some ideas about that that said that this thing should be stable. Turns out it's not. Is that they care about publications. It's not necessary for you to stay in the place that you were, sort of in the research area that you were hired for. So I was able to spend some time working on what I would call safe problems. I was able to spend some time working on things that were purely exploratory. So here's one example of a safe problem. Up top, I was imagining something that was stuck in one of those potential walls in one of those optical traps. You can, as you probably know, you can follow the position of the object in one of those optical traps as a function of time. You can come up with a probability distribution for displacement. So this is sort of a histogram of the number of times we found that object at a certain distance from the center of the trap. And that was the distance from the center of the trap. And if you take the inverse logarithm of that, you get the potential. Great. And out of this, just like everything else that you find, at this level, it's a simple harmonic oscillator. You can pull out the spring constant. You can study the distribution of spring constants and find out, how uniform your particular algorithm is in producing traps. I did this. I did some non-equilibrium self-assembly stuff. The other thing I did was I was talking with a computer scientist about problems that they encounter. And one of the problems is you're building this three-dimensional model, right, that you'd like to show and have be as real as possible. The question comes with, what do you do when light hits the surface of that model? Right? You'd like to have a function that says, what's the probability that a ray that hits at a particular angle bounces off at a different particular angle? So you can do a ray tracing ad infinitum. The state of the science there is that there are a bunch of models that people do, saying the surfaces are complex. Let's make a model of what the interaction of those complex surfaces is with light, and let's see if that gets the right answer. Right? It turns out they come damn close. Right? What people didn't do was they didn't say, let's do that measurement, and let's go in and see if the surface really looks like what we said it looked like, which leaves a sort of obvious hole to check. And it was something that, as a microscopist, I could look at and work well with a computer scientist. This one's a fun problem. It's just meant to be a sort of mind cue for me. And I'll just I can't resist, I really like this problem. Okay. The western shore of Ireland has a lot of big cliffs on them, right? And you get to this cliff, there's no hill before you get to the cliff. You get to the cliff goes down tens of meters into the ocean. Right? So let's say this drop is 50 meters and about halfway is where the ocean is. You get there and you find there are these huge boulders. Huge boulders can mean things that are merely tons, things that are tens of tons. And the question is, where did those boulders come from? Right? The most obvious answer is they came from the sea. Then you have to find something that can lift hundreds of tons from the bottom of the sea up to on top of this cliff. Clearly, nothing but a tsunami can do that. And so if you can date when those boulders got there, you have a record of when tsunamis were. And that's important because if you're going to, especially now, if you're going to have a good model, you're going to test your model of like what's going to happen when the United States leaves the Paris Accords. And you're going to predict extreme weather events. You'd like your model to be able to get the right answer for extreme weather events that happened in the past, right? So this model that says a tsunami took a 100-ton boulder and put it on top of a cliff, right? That's important. And that's all reasonable and wonderful until you talk to people who live in Ireland, who will point to that 100-ton boulder and say, that wasn't there before 1992. So either there was a secret tsunami in 1992, or your ideas are bullshit. Right? So you have to come up with something else. And so being able to characterize these well is important. And so I was able to work on that too. And I got a free trip to Ireland. Okay. So yeah, even at a small college, you have to write grants, and you're busy, right? Because you have to teach. I mean, I was in a sweet position. I had to teach twice as much as Heinrich did. Most other folks at small colleges have to teach 5 times as much as Heinrich did. But the standards are high, and you have to do research. And I was looking forward to like dropping a little bit of one of those things. If I could drop writing grants, awesome. So I started thinking about what to do next. And again, like, this is part of the exploration. Trying to figure out what to do next. But I was also having conversations with a bunch of other folks. Is everyone going over? And here are some things that I thought about. I thought about science writing, especially in physics, because I read sort of popular physics writing and I cringe a lot. Those of you who know me know I really like food. Thought about food science. I thought about technical consulting. I really like stability. I really like just going to work and doing my thing, right? And with this, you really have to hustle and find clients. So that left high-tech companies. I explored some. This guy was interesting. The way that I did exploration in these two bubbles was, and in all the bubbles actually, was this same thing of just having conversations with people. I happened to have met a science writer, somebody who was writing fiction, but was like encouraging me to go down that road. But here, if you remember before, I said I was collaborating with a computer scientist. Turns out he consulted. He's now an employee of NVIDIA, but he consulted with NVIDIA at that point. He said, look, if you like this stuff, I should get you in touch with a couple of folks. So he got me in touch with somebody at NVIDIA, he got me in touch with somebody at Google. I had a friend from college, he got me in touch with somebody from Microsoft. I just went down the road and just had conversations with people. And this one with NVIDIA went really well. I got to this point of working on more and more complicated ways of calculating phase-only holograms. At some point I said, why am I doing this? Turns out an amplitude hologram is cheap. I should just put it in the optics, right? At which point I felt really stupid, honestly. But when I told the folks at NVIDIA that I wanted to put an amplitude and phase hologram together, minds blown. Like, I had no idea that like this was going to be interesting to them. Turns out it's incredibly interesting to them. You might ask why. Okay, I'm going to have to step back a moment and talk about head-mounted displays. NVIDIA is interested in head-mounted displays, augmented reality and virtual reality, for reasons that you know about, right? What they really want to do, and a bunch of people really want to do, is they want to take all the screens in your life and make them go away, and replace them with augmented reality and virtual reality. You might say, look, my computer works just fine. Right? But imagine you put one of these things on and you have a screen that's this big, wherever you are, right? Even in your airplane, right? And it's at some comfortable distance. You can spread everything out. Even better, I wouldn't have believed this when I was a grad student. Turns out my office when I was a grad student, much better than my office now. No. Yeah. Depends on your personality. I'm an introvert. You couldn't tell for now, but I'm acting. At NVIDIA, I'm in cubicle hell. If I could put something on and I could virtually be doing my work from Tahiti, amazing, right? So that's another reason to do that. That demands that you be able to wear one of these things for 8 hours, right? And if you've ever played with one of these things, you're not going to wear them for 8 hours, right? And I can think off the top of my head of like 3 reasons why. Your head's going to hurt. I suppose the second reason is your head's going to hurt. So your head's going to hurt just because you've got this thing that's hanging off your head, and it's going to be dragging your head down, right? It's not. Today they're not well balanced, they're not even light. The other reason why, and we'll get to this why, is the method of making images for you is bad currently. And then the last reason, probably most people in this room wouldn't suffer from this, a lot of people won't wear this because it's not fashionable, right? And that's going to kill your market. So why the imaging is bad is it turns out in the real world, two things happen when you look at something at a distance. Your eyes tilt in, right? And the lens in your eye changes focus. And it turns out those two things are tied together physiologically, right? If you go to a 3D movie, there's a screen there, right? And what they do, what everybody does now, is they just show each eye a different image. And the disparity between the images is supposed to it's supposed to change the vergence of your eyes such that you see something further or closer from you, but you still have to focus at the display. These are eyes, this is the display. This is supposed to be where you're focusing. That's where your eyes are verging to. That takes effort, and it causes a lot of people headaches. Right. So what you'd like to do is, even if you don't put the real world here, you'd like to enforce that your eyes would verge and focus to the same place. Right? There are a number of ways of doing that. Here's one way. Now we're getting to the work that we're doing at NVIDIA. Right? If you can take an object and make a virtual image of that, that is, as far as you're trying to make your eyes verge, you're done. Same thing. Right? Now we'd just like to make it light. So this is one way of trying to do that. And this is sort of complicated, so I'll try to step through this carefully. This thing is supposed to be an eye. Right? This is a projector. That's a screen that turns out to be a hologram. Here's basically a half-silver mirror. What we're trying to do here is make an image on this hologram, have the hologram redirect light directly towards the half-silver mirror that is curved, so it acts like a lens as well as reflecting the image back to you, and then have that just pass through the hologram. Right? Most optics won't do that, but holograms will, because the light that's coming back through doesn't solve the Bragg matching condition that would allow this thing to act like a diffraction gradient. What's happening over here, and so that ends up creating a virtual image that's out here, that's far enough away from you, that it can be at the same place where your eyes are verging to. And because this is just a flat sheet of plastic or glass, this is more or less the same, the whole thing is much lighter. This is just an image that we took of one of the holograms to show that it does what it's supposed to do. Right? This thing with the light engine, that's just a projector. So here's light from the light engine. It's not a perfect hologram. So some light leaks straight through. For our observer, that doesn't really matter much. For other people who might have you wearing these glasses, you might be wearing these glasses in front of, as long as the light's not too powerful, that's not too bad either. Actually, it's kind of nice because it allows people to see what you're seeing. So that means that you can't pull up secret information about them. Right? What you're supposed to see here, it's kind of light here, is that some light diffuses away from the hologram in a way that is not what you would expect from normal optics. Right? But if we have light that comes from the rest of the world, or comes from the mirror, it sails straight through without the extra diffraction. Right? So that means if I got a tree out here, the person sees the tree as well as the information we put on it. Okay? Here's what it looks like on a model. Still kind of goofy. We thought we might go for a steampunk vibe. So no, this is still just research. I can't promise that this is going to be a product at all. We're just making stuff. Here's how it works outdoors. Right? So we can put an image of a teapot in front of a building in bright daylight. Right? And if you can do that in bright daylight, you can do it indoors as well. So that's work I do with things that are called holographic optical elements. They're just little elements that themselves act like bits of objects. Turns out you can also do programmable holography. We've done a bunch of work like that. I'm going to speed through this guy because I'm running way late, and I apologize. But essentially, we've spent some time figuring out how to calculate holograms well. This is our result for calculating a hologram. Here's what the previous state of the art was. Right? So this is just a screw that's seen in space. Here's the calculation of what we think we should see, the simulation. Here's what you actually see in a camera. Here's what you see when you focus at the beginning of the screw. Here's what you see when you focus at the end of the screw. Notice that wherever you're focusing, the place that's farther away from where you're focusing is out of focus. You can even make, and if you have a standing hologram, right, you can take, oh, forget about the sign. Here is a set of a hand, another hand, and a ball. We're just changing the focus of the camera to show you that there's depth information in there. Right. So this thing, that hologram basically creates the configuration of light, the so-called light field, that you would see from the actual objects. Okay. So basically, what I said was, if you think that this is something you might want to do, sort of explore something that's not academic, spend some time now exploring that. Right. Heinrich was really supportive of that. I suspect that your advisor will also be supportive of that within reason. And when you're looking for something, you just spend a lot of time talking with people. Just go out there and say, this is what I'm interested in. Can you point me in the right direction? And the questions should always be essentially that. Never ask somebody for a job. It's just bad form, right? If somebody's interested, they will say, you should apply, or I think I should hire you. And that will just happen because as you're having conversations with people about the same thing, you'll be gathering information that suddenly makes you the smartest person in the room. Okay? Yeah, and you just basically, you look for what you want, and you find it. Okay, sorry about going so far over. Any questions?
So when is this coming out, Ward?
Those two results were submitted to SIGGRAPH Asia. We're waiting to hear back from them. So the way that these things work is slightly different. There's like a deadline for a conference, and everybody goes crazy trying to get to that deadline, and you have to have the paper at the same time that you submit. Like you submit the paper. So we've got maybe a couple of months to find out if those two results were accepted. And then if they were accepted, then the stuff will come out basically end of the year.
But what I really was after, when can I buy one?
I don't know the answer to that. Right, I mean, so the timeline on which research works is that the shortest timeline, or rather, the shortest timeline in which anything in my group would come out is basically 2 to 3 years after we're done with it, right? Because research, if you think of this in terms of risk, the research folks show what's possible, right? And then it has to be made robust, right? So, right? This thing works, but we wouldn't want you to take it and just from 3 feet above the floor drop it, right? Because that would take these mirrors and really screw them, right? So the the product folks have to make a solution that works robust. Nathan?
Would you interface with those folks? Like, did they, what, can you say a little bit more about the process of actually having that work, or is it totally out of your hands?
No, well, yeah, it sort of depends on the researcher. But for other things that have gone from research to product groups, there have been basically two ways of technology transfer at NVIDIA that have worked. One is the easiest way of taking that knowledge. So you take the researcher out of the research group and you put them in a product group. Right. The other way is you get people from the product group to basically join the research group for about a year. Right. And they, sitting next to each other, they like work through the details. Like, sorry, why doesn't this hologram work this way? And it's like, well, because you're using the wrong settings. Right. Do I have to use those settings if I'm going to make 100,000 of them? No. Right. There are other processes of replicating holograms. Here's what you need to know. Cool. Thanks for your patience.